Do you know what powered a major industrial city for nearly a century without a single wire strung overhead? Without transformers on poles? Without electrical substations every few blocks? Without any of the visible infrastructure we associate with modern power distribution? The answer sits beneath the streets of a city most people have walked through without knowing it existed there. I discovered this while researching something completely different, following a thread about pre-electrical infrastructure. Try to understand how 19th century cities managed energy before the grid. A reference appeared in a footnote in an obscure engineering journal. The system was described in 3 sentences. I assumed it was a failed experiment, something that operated for a few years before people realized it was impractical and switched to the obvious solution of running wires. I was wrong about nearly everything. The system was called the London Hydraulic Power Company Network, though the principle itself wasn't unique to London. What made it remarkable was the scale, the duration, and the absolute completeness of its erasure from public memory. The company was incorporated in 1871. It began supplying power commercially in 1883, operating from a pumping station at Grosvenor Road in Pimlico. The engineering principle wasn't complicated. Water was drawn from the Thames, purified, and pressurized to 750 pounds per square inch. That pressurized water was then forced through a network of cast iron mains buried beneath the streets of central London. Not cables, not wires, not distributed generators on every block, just pipes, thick-walled cast iron pipes manufactured to withstand pressures that would burst ordinary plumbing. For inches in diameter for the distribution mains, they ran beneath the roadways, completely invisible to anyone walking above them. You could stand directly over an active main carrying full system pressure and feel absolutely nothing. The system made no noise. It generated no heat. It left no trace at the surface. What that pressure moved is what I keep returning to. The bascules of Tower Bridge, each weighing approximately 1,000 tons, were raised and lowered by hydraulic power for 82 years. The lifts in the Savoy Hotel operated on it. The printing presses along Fleet Street ran on it. So did the hoisting cranes at the London docks, the stage machinery at the Palladium, the hydraulic jacks that set the foundations of the Ritz Hotel, the mechanisms inside the clock tower at the Palace of Westminster, the goods lifts in the department stores along Oxford Street. These were not marginal applications. They were not demonstrations of an interesting engineering principle. They were the operational core of some of the most prominent and economically important buildings and working sites in Victorian London. The engineer most responsible for making city-scale hydraulic distribution actually work was Edward Bayzand Ellington. His critical contribution was a hydraulic accumulator, a weighted cylinder that maintained constant system pressure even as demand across the network fluctuated wildly. The principle was simple. A heavy weight sits atop a water-filled cylinder. The weight presses down continuously. The pressure it generates remains constant regardless of whether one customer or 100 customers are drawing power at any given moment. Ellington's versions were some of the largest ever built. Cylinders rising to the upper floors of pumping stations. The weight suspended on columns of pressurized water around the clock. Every day, for decades, new pumping stations were added at Falcon Wharf, at City Road, at Whitehall, and at Rotherhithe as the network expanded. By its maximum extent, the system covered 184 miles of mains and delivered the continuous equivalent of 8,000 horsepower across an area stretching from Whitechapel to Kensington. That was approximately the size of Manhattan, powered by pressurized water flowing through buried pipes. I should be clear about something. This was not a perfect system. It had a structural vulnerability built into its economics from the beginning. The customer base was always skewed toward large industrial and commercial users. A dock warehouse, a newspaper press room, a factory floor. The fixed cost of maintaining 184 miles of pressurized pipe was enormous. That cost had to be spread across a relatively narrow base of clients. Narrowness mattered. One large customer canceling a contract was not equivalent to losing a handful of domestic accounts. It was a significant fraction of a revenue that kept the entire network viable. The company's engineer in the 1890s reviewing subscription figures described customer concentration as a structural risk in an internal memorandum. He used that phrase without warning or alarm. Not a warning, a fact about the system he ran. Then, continuing his day, The language was clinical. The implication was understood. The network could tolerate gradual growth. It could not tolerate sudden departure by major clients. In 1890, the first electrical power stations in central London began operation. The hydraulic network was 37 years from its end. The electrical grid was just beginning. For the next 9 decades, both systems would run simultaneously beneath and above the same city streets, serving sometimes the same buildings, sometimes the same customers. Electricity did not immediately win. It did not win quickly. The assumption when electrical supply companies began multiplying across London in the 1890s was straightforward. Newer technology displaces older technology. Current replaces pressure. The hydraulic network would contract and disappear. It did not disappear. For nearly 90 years, the two systems ran side by side. For much of that time, hydraulic held advantages that electricity could not simply argue away. Not electricity, not fire risk, not electrocution. Those 3 words kept hydraulic power contracts in place long after electric motors were technically available to replace them. Fire first. Warehouses storing cotton, grain, paper, and dry timber had precise reasons to avoid electrical equipment in the early decades of the electrical industry. A faulty motor in a building full of combustible goods was not a theoretical concern. It was a calculation made by insurance underwriters and warehouse managers simultaneously. Hydraulic motors carried no such risk. The pressure did the work. There was no current, no arc, no heat source. The Port of London Authority ran hydraulic cranes along the dockside long after electric alternatives existed for exactly this reason. Electrocution second. The early electrical grid was not the standardized, well-insulated system that exists today. Voltage standards varied between supply companies operating in adjacent districts. Accidents were frequent enough to be documented regularly in technical journals. A hydraulic connection was a sealed metal pipe. The worst failure mode was a water leak. That was a maintenance problem, not a mortality event. Reliability third. The hydraulic network ran on water. Storms did not interrupt it. A lightning strike on a generating station did not affect it. Then, beginning in September 1940, something more serious than storms arrived over London. During the Blitz, several Fleet Street newspaper offices continued operating their hydraulic presses through periods when electrical supply was disrupted by bombing damage to the grid. The physical redundancy of the buried pipe network, multiple pumping stations, multiple supply routes to the underground mains gave a resilience the centralized electrical infrastructure could not always match. The hydraulic system had no single point of failure that an incendiary device could locate. It was distributed. It was underground. It was in the specific and unexpected way better suited to bombardment than its replacement. A company report from 1930 recorded 5,000 active connections across central London, delivering 8,000 continuous horsepower through 184 miles of mains. That figure was essentially stable across a decade, not growing, not collapsing, holding. Here is where the story becomes strange. The hydraulic network was not superseded because it failed. There was no engineering catastrophe. No fatal design flaw revealed itself after decades of operation. The pipes did not corrode beyond repair. The accumulators did not become impossible to maintain. The system that was switched off in 1977 was, by the technical assessment of its own engineers, still functioning correctly. What happened was considerably more ordinary and in a way more troubling than failure would have been. From the 1950s onward, customers began leaving, not in a rush but gradually. A dockside warehouse modernized its equipment and switched to electric cranes. A newspaper press room was rebuilt around new machinery. A hotel renovated its lifts. Each individual decision was rational. The economics of electrical supply had matured. The capital cost of switching had fallen. One by one across 2 decades, the large industrial customers who anchored the network's revenue made sensible choices for their own operations. The fixed cost of maintaining 184 miles of pressurized main does not fall proportionally when you lose a third of your customers. The pipes still require inspection. The stations still require staffing. The pressure must be maintained continuously because a hydraulic network cannot be throttled down to match reduced demand. You maintain full system pressure, or you do not maintain the system. The physics do not allow half measures. By the mid-1960s, the London Hydraulic Power Company faced a calculation with only one outcome. The infrastructure required to serve the remaining customers was the same infrastructure that had once served 5 times as many. Revenue had contracted. Costs had not. The board could see where the line was going. In 1977, they followed it to the end. The decision to cease permanent operations was recorded in board minutes with a register of a routine administrative closure. A Victorian utility retiring a depreciated asset. The language used was precise, practical, and completely incommensurate with what was actually being closed. 94 years of continuous operation. 184 miles of functioning infrastructure. The mechanism that had lifted Tower Bridge 500,000 times. Wound down in language that would not have been out of place in the closure notice for a small regional gas supplier. The last pump ran at Grosvenor Road in Pimlico, the same address where it had all begun 104 years earlier. The Tower Bridge detail is the one that stays with me. Tower Bridge had been powered by hydraulic since the bridge opened in 1894. The machinery was housed in the bridge's own accumulator towers, fed from the London Hydraulic Power Company's mains running beneath the embankment. In 1976, 1 year before the network closed, the original hydraulic mechanism was replaced with electro-hydraulic rams. The announcement used a language of routine modernization. The press coverage was minimal. 82 years of continuous operation, ending in a paragraph in a trade journal. Retired without ceremony 1 year before the company that had powered it was itself retired. George Ogden, one of the final engineers at the Grosvenor Road station, described the last month of operation as ordinary work. The accumulators performed as designed. The pumps ran on their usual schedule. The pressure held at 750 pounds per square inch as it had held for 94 years. Nothing was failing. The system was not deteriorating. It was turned off while it was still working correctly. That detail has stayed with me since I first encountered it. The pumping stations did not outlast the closure by long. The Grosvenor Road building in Pimlico was converted to other uses. The Rotherhithe Station, a substantial Victorian brick structure on the north bank of the Thames, eventually became a nightclub and later a residential development. The Bankside Station at Falcon Wharf was demolished. The City Road Station is gone. Within a decade of the final shutdown, the physical infrastructure, one of the largest hydraulic power networks ever constructed, had been dispersed, repurposed, or erased. Not all of it. Some of the pipes are still down there. Not every section was excavated. Across central London, beneath roads and pavements that millions of people cross daily, sections of the original cast iron main remain in the ground, sealed and inert. They are not marked on standard utility maps. They are occasionally encountered by workers excavating for new cable or water installations, identified by their distinctive thick-walled profile and left where they are. The work continues around them. The pipes remain. Maybe this is just the ordinary history of infrastructure. A utility reached the end of its economic life and was wound down in the normal way. A board made rational decisions. Ancient iron outlasted its usefulness. Except I cannot stop thinking about how quickly the knowledge disappeared. Within 15 years of 1977 shutdown, the working expertise required to operate a city-scale hydraulic power network had ceased to exist as a living body of knowledge. The engineers retired. The operational records were archived where they survive at all. The specific understanding of how to manage pressure across 184 miles of interconnected main, how to respond to a leak, how to balance load between stations, how to maintain accumulator performance through winter and summer variations, was not passed on to anyone. There was nothing left to apply it to. The word hydraulic comes from the Greek hydraulis, a water pipe organ invented in Alexandria in the 3rd century before the Common Era. We still use the word. It appears in engineering, in finance, in management. Hydraulic pressure, pressure points, systems under pressure. The vocabulary survived intact. The specific application it once described, running silently beneath the streets of central London for nearly a century, has gone from living memory. What replaced the hydraulic network was not uniformly better. It was cheaper to maintain once the electrical grid, had already been built, and its capital cost was sunk elsewhere for certain applications in fire-sensitive environments, in spaces where silent operation mattered, in industrial settings where a water leak was preferable to an electrical fault. The trade-offs were real. They were not widely discussed at the time. The economics had decided before the engineering argument could be properly made. The questions I cannot resolve are these. Why were no pipes preserved as a functioning heritage section when industrial conservation groups were active throughout this period? Why did the knowledge transfer happen with so little documentation? What would a working hydraulic network mean in a dense modern city where silent and spark-free power delivery in confined spaces has obvious value? What remains unstudied in the company's operational archives? And why? When you stand on Tower Bridge and watch those arms rise, does almost no one know they ran on water pressure for 82 years? The system that fed them was wound down so quietly, it left almost no trace in the public memory of the city it had served for nearly a century. The pipes are still there beneath the streets, cast iron, sealed, inert. The pressure is long gone. The language remains. And somewhere in London, someone walks above 184 miles of history without knowing what they are walking on. The city remembers only what it chooses to see. Everything else is buried,